At last, we come to the definition of continuity. This module is probably the most important one in this entire course, so I suggest you turn off WhatsApp, grab a cup of your favorite beverage, and concentrate for the next 30 to 40 minutes. I am going to state a theorem that characterizes various notions of continuity. Theorem. Notions of continuity. Let A be a subset of R and f from A to R be a function. Fix x in A. The following conditions, or rather the following statements are equivalent. The first statement: for any subset B of A such that X is adherent to B, we have f of X is adherent to f of B. If you recall, this is almost exactly the informal notion of continuity that was stated earlier, with one difference: the word in quotes close has been replaced by the word adherent. Number 2. If xn in A converges to X, then f of xn converges to f of X. Okay? And the third one, which is called the epsilon delta criterion, which is the reason for nightmares for thousands and thousands of math undergrad students throughout the world. Let me state this precisely. The epsilon delta criterion is as follows. For each epsilon greater than 0, we can find delta greater than 0 such that if y is in A and mod y minus x is less than delta, then mod f of x minus f of y is less than epsilon. Okay. Now, I have stated 3 statements and I am saying that the following are equivalent. That means whenever one of the statements is satisfied, the other 2 statements are also automatically satisfied. Now, I call these notions of continuity because these are 3 good ways of trying to formulate what a function f being continuous at the point x really means. The first one we have already explored at some length. In a moment it will be clear to you that the second one is just a slight variant of the first. But the third one deserves some comments, as that is the standard definition of continuity given in most places. So I will dedicate an entire module to the third one. Now what I am going to do is I am going to prove that all 3 statements are equivalent. then I recommend that after watching the next few modules, you revisit this module yet again. In fact, I would strongly recommend that this module be watched at least 3 times to digest what exactly is going on. Okay, proof. Now, the standard way of showing that 3 statements are equivalent is to show that 1 implies 2 implies 3 implies 1. That is, form a complete circle. Let's see how we can do that. Let's look at the first statement. For any subset B of A such that X is adherent to B, we have f of X is adherent to f of B. The second statement, we have to show that if Xn in A is a sequence that converges to X, then f of Xn must converge to f of X. Okay. So assume 1 is true and let Xn in A converge to X. We have to show f of Xn converges to f of X, right? So far all I have done is rewrite the thing that I am supposed to do. Okay. Note that Xn, this is the set Xn. So let me be ultra precise what this set is. Note that the set B, which is defined to be Xn such that n is in N. Okay, I am considering all the points in the sequence Xn. Note that the set B as X as an adherent point. Well, that's because Xn converges to X. That's the very definition of an adherent point. Okay, that means the set f of Xn has f of X as an adherent point. Okay, adherent point, right? That's what our assumption 1 is. Whenever you have a set that has X as an adherent point, the f of B should have f of X as an adherent point. In this case, f of B is nothing but f of Xn. Our aim is to show that f of Xn converges to f of X. So what we are going to do is the following. So let me just write down the aim so that it's in our mind. Aim to show f of Xn converges to f of X. Okay. So now how we are going to do this is a slightly roundabout way. We will show that any subsequence f of X and K has a further subsequence that converges to f of X. Okay, recall that in the chapter on sequences and series, we had shown that if a sequence has the property that any subsequence has a further subsequence that converges to a particular point, then the whole sequence converges to that particular point. So we are going to exploit this result. Okay, so start with a subsequence. Subsequence f of X and K. Okay. Now, there are two possibilities. Either number 1, f of x and k equal to f of x infinitely often. So that means for infinitely many k, f of x and k equal to f of k. Then we are done. I'm not even going to bother writing down how we are done. I'm going to leave it to you. Okay. So the second case is f of x and k is equal to f of x for only finitely many k. It's a pure dichotomy. Finitely many k. This is the case we have to deal with. So if f of x and k equal to f of x for only finitely many k, then you cannot extract a subsequence in the easy manner that happened in case 1 when there were infinitely many k's for which f of x and k equal to f of x. You will have to do something else. Observe that in this scenario, f of x is in fact a limit point. Why? I'm not going to tell you why. It's up to you to figure this out. Okay? That means there is a sequence y, let's say I use a different subscript ym, coming from the set of elements f of x and k such that the yms are distinct and ym converges to f of x, right? This is the very definition of a limit point, right? Okay, now I'm going to use this ym to construct the required subsequence. Okay, so observe that each ym is of the form f of x and k for some k. I don't know what that is. Okay, for some k. Okay, excellent. Now this is how I'm going to construct the subsequence. Choose what I will do is the following. I will construct a subsequence of ym which itself would be a subsequence of fx and k as well. Okay, so choose y1 to be not y1. Let me give a better notation. I will produce a sequence, let's say some zl, which will be a subsequence of both ym as well as fx and k. How do I do that? Well, choose z1 to be fx n, let's say L1 equal to y1. Okay, so this y1 will necessarily have to be of the form f of xn L1 simply because these yms are coming from the set f of x and k. I just choose y1 to be that. Okay, now as the terms in the sequence ym are all distinct, okay, there must be some ys s greater than 1 such that ys is equal to f of xn L2 and L2 is strictly greater than L1. Okay. Note, the terms of the sequence Ym are all distinct. Okay. So it cannot happen that the terms of the sequence keep oscillating all the way less than f of x and L1. Where, I mean, what I mean to say is, it cannot happen that the terms of the sequence Ym are all elements of the set f of x and k less than or equal to L1, right? Then there will have to be repetitions because this is a finite set. At some point, Ys has to be f of x and L2 and L2 is greater than L1. Set this Z2 to be nothing but this f of x and L2. Okay. So having constructed Z1, Z2 up till, let's say, Zr, then choose, and this Zr I'm going to call it f of x and r. Okay. Then choose Zr plus 1 to be some Yj equal to f of x and j with j greater than r. Okay. This is possible because the set f of x and k less than or equal to let me just change the notation slightly. Here I need to use two subscripts because it's a subsequence. So this is an LR. Okay. K less than LR is a finite set. Okay. So this is a bit complicated, what is happening, mainly because there is a notational overburden. That's why I want you to watch this module at least once or twice more after you come to grips with the basic facts about continuity in the next few modules. But basically what we have done is to somehow construct this subsequence of both Ys as well as f of x and k. Right? Now we have constructed a subsequence of both Ym as well as fx and k. We have sort of a common subsequence of both these sequences. Okay. But Ym converges to f of x, and therefore so does, what did I call this? Well, let me just call it the sequence Zr. So does the sequence Zr. Okay. Hence we have found a subsequence, or rather, a subsequence of fx and k that converges to fx. So in both scenarios we have found a subsequence of fx and k that converges to f of x. So conclusion is f of xn must converge to f of x. Okay, so this was a somewhat long and arduous proof, but the basic idea is really easy. We deal with two cases. The first case in which you don't have to do much work, you can find a very simple subsequence that converges to f of x. Then in case you cannot find a simple subsequence that converges, you are forced to conclude that f of x is a limit point that gives us a sequence of unique terms. Using this unique term sequence ym, you construct a common subsequence, and that does the trick. Okay, so please go through this proof carefully once more. So what have we achieved? We have now shown that 1 implies 2. That means if it is true that whenever x is an adherent point of a subset B, we have f of x is an adherent point of f of B, then for all sequences xn converging to x, f of xn must converge to f of x. Okay, excellent. Now 2 implies 3. That is, whenever you have a sequence xn converging to x in A, then f of xn must converge to x. Okay, so now we are in the case 2 implies 3. Okay, now what does 3 say? Let me read out 3 carefully. 3 says, for each epsilon greater than 0, we can find a delta greater than 0 such that if y is in A and mod y minus x is less than delta, then mod f of x minus fy is less than epsilon. Now this is very reminiscent of the definition of the convergence of a sequence. So what do we do? Well, think about this for a second. How can 3 fail to be true? The only way that 3 can fail to be true is for some epsilon greater than 0, we cannot find delta greater than 0 such that something happens. Okay, that means for some epsilon greater than 0 and for all delta greater than 0, there must be a point y in A and mod y minus x less than delta such that mod f of x minus f of y is greater than epsilon, right? So let's see how to do that. Assume 3 is false. Then for some choice of epsilon greater than 0 and all choices of delta greater than 0, we can find, rather than writing all choices, so for some choice of epsilon greater than 0 and each choice, rather than writing all, I will use each. It will clarify things better. Each choice of delta greater than 0, we can find y in A such that mod y minus x is less than delta, but mod f of x minus f of y is greater than or equal to epsilon, right? No delta works, so for each delta there must be some y that plays spoil sport. Okay, that plays spoil sport. Okay, now how do you do this? Well, this can be done for each delta equal to 1 by n. Okay, each delta equal to 1 by n. So what this means is we get call the corresponding points, spoil sport in quotes, spoil sport points yn, that is mod yn minus x is less than 1 by n, and mod f of xn minus f of x is greater than or equal to epsilon. Okay. Now clearly yn converges to x, right? That's how yns were constructed. Mod yn minus x is less than 1 by n. Therefore, yn converges to x. But f of xn minus f of x is greater than or equal to epsilon for all n. This means f of x is not an adherent point of the set f of xn. Okay. Okay, just a moment. I got ahead of myself. I tried to prove 1 from this. Well, I don't want to prove 1. I want to prove 3. Okay. Okay. But clearly f of xn cannot converge to f of x. I tried to contradict 1. In fact, 1 is contradicted, but I want to prove that 2 is contradicted. That's also good enough. Clearly, f of xn cannot converge to f of x. Hence, 2 is contradicted. 2 is contradicted. Okay. Hence 2 implies 3. Finally, we have to prove that 3 implies 1. Okay. That means we are assuming the epsilon delta criterion. We have to show that whenever we have a subset B such that x is adherent to B, we must have f of x is adherent to f of B. Okay, let's prove that. Assume 3 is 2. 3 is true. Okay. Let B subset of A be such that x is adherent to B. Okay. Now we must show that fx is adherent to f of B. Again, I have just written down what is it that I must achieve. Okay. Now, since 3 is satisfied, for each n in the natural numbers, we can find delta n such that if mod xn minus x is less than delta n, then mod f of xn minus f of x is less than 1 by n. 3 says that for each epsilon greater than 0, there is a delta such that something happens. Okay. What I'm doing is I'm taking epsilon to be 1 by n and taking the corresponding delta to be delta n. Okay. So, such that, okay, I made a mistake, such that if mod y minus x is less than delta, then f of y minus f of x is less than 1 by n. I haven't really constructed an xn yet, but x is adherent to the set B. Therefore we can find xn in B such that mod y minus xn is less than delta n, right? Simply because this is one of the properties of adherent points. Okay, but this means mod f of xn minus f of x is less than 1 by n, right? That's what the previous condition, that's what delta n, that's how delta n was chosen. In other words, f of x is adherent to f of b. Fine. So this completes the proof. I hope you enjoyed the cup of coffee and some difficult mathematics. So this is a long proof. As always, please go through the notes where things are done. This is a lecture, so I cannot just copy the notes and put it in the lecture. I am lecturing from my mind. So best to go through this as well as go through the lecture notes where things are done more precisely without any slip-ups on my end. I'm sure with the help of this lecture as well as the notes, you will be able to understand why 1 implies 2 implies 3 implies 1, and all three definitions here are equivalent. Okay, so let's end the lecture with our reward. Our reward is at last the central thing, the definition of continuity. Definition of continuity. Let f from a to r be a function and x in a. We say f is continuous at x if 1 and in parenthesis and therefore all of 1, 2 or 3 in the previous theorem is satisfied. Okay, so please again go through this lecture at least once or twice more. Do it once again after a few more modules where you see many continuous functions and some theorems about continuity. So this concludes this module. This is a course on real analysis, and you have just watched the lecture on notions of continuity.